Okay, so the next question that we have here is example number 10. Example number 10, which is basically show that the function f from n to n, you want to show that f from n to n is given by f of 1 is equal to f of 2 is equal to 1, given by f of 1 is equal to f of 2 is equal to 1, and f of x is equal to x minus 1. F of x is equal to x minus 1 for every x greater than 2. For every x greater than 2 is unto but not 1 1. Is unto but not 1 1. Okay, so what this means is that basically f of 1 is equal to f of 2 is equal to 1, which means that it's not a 1 1 function, right? Because a 1 1 function is the kind of function where distinct elements of the domain have distinct images in the range, which is not the case here. Basically, in this case, you can see that 1 and 2 are distinct elements of the domain, and both of these elements have one single image which is equal to 1, as you can see here. And so therefore basically the function is not 1 1, right? Now about the fact that it is unto, of course you can imagine that unto means that basically every element of the codomain is the image of some element in the domain of the function, right? So what that means is that basically, so we are working with a set of natural numbers, so 1 is mapped to 1, 2 is also mapped to 1, and then for example 3, which is some x greater than 2, is mapped to x minus 1, which would be 3 minus 1 is equal to 2, right? And then 4 is again mapped to x minus 1, which means that it's mapped to 3. 5 is mapped to 4, and so on and so forth, right? So that means that every element in the set of this is the set of natural numbers, and this goes all the way up to n. So this is the set of natural numbers, and this goes all the way up to n, and this is also the set of natural numbers, right? So as you can see, every element in the domain of the function is of course mapped to some element in the codomain of the functions, which means that this is first of all a function, and meaning that no element here is left out. Second of all, the function is not 1 1, because as you can see here, basically 1 is mapped to 1 and 2 is also mapped to 1, which means that basically these two distinct elements of the domain do not have the two distinct basically images in the range, which means that the function is, well, not 1 1, right? Now this is unto, because as you can see, as this shows, basically 3 is mapped to 2, 4 is mapped to 3, 5 is mapped to 4, 6 is mapped to 5, and so on and so forth. Meaning that in the same manner, basically every element of the set of natural numbers, as far as the codomain is concerned, is going to be the image of some element in the domain, meaning that there is all of the elements here in the set of natural numbers will simply be covered. And so what that means is that, of course, this is an onto function. Now let's read the solution once as well. Okay, so as far as the solution is concerned, basically the solution is a much more elegant way of saying the same thing that I said, and of course what I said is no logical proof. So basically you need to state the same thing in a logical manner, and that's basically how you say it. So basically you have, of course, about f being not 1, 1, we have over here we have f of 1 is equal to f of 2, f of 1 is equal to f of 2, which is equal to 1, meaning that distinct elements of the domain do not have distinct images in the range, as is the case with 1 and 2, and therefore basically f is not 1, 1, right? So f is not 1, 1. Now about f being on 2, you have to show that every element in the range of the function is simply an image of some element in the domain of the function. Okay, so that's what you need to show. So over here what we have is that the rule of the function tells us that for every x greater than or equal to for every x greater than 2, we have this rule for the function. We have f of x is equal to x minus 1 for every x greater than 2. For every x greater than 2. Now, as you can see here, basically what happens is that 1 is covered by this part of the rule of the function, meaning that you have f of 1 is equal to f of 2 is equal to 1, right? So basically f of 1 is equal to 1, right? F of 1 is equal to 1. So that means that 1 is already covered here. We have no problem with 1. About all the numbers, basically, about all the numbers in the range of the function not equal to 1, we can say that for every basically y belonging to n and y not equal to 1, basically what we have here is f of x is equal to x minus 1. We have f of x is equal to x minus 1. If I take f of x as y, if I take f of x as y, then that means that basically y is equal to x minus 1, right? And so what that means is that I can calculate x in terms of y, meaning that I can write x is equal to y plus 1. I can write x as y plus 1. Then that means that for every y belonging to n in the range of the function, or in the codomain of the function, I should say, since f of x is equal to y, we can write basically x is equal to y plus 1, right? And x is equal to, so f of y plus 1 is equal to basically y, which is equal to x minus 1, and of course, I'm sorry, f of x here is supposed to be, of course, f of x is supposed to be basically x minus 1. Now, if I write x as x plus 1, if I write x as y plus 1, so f of y plus 1 is equal to x, which is equal to y plus 1, and you have a negative 1 over here, so these two will be cancelled out, and so you have f of y plus 1 is equal to y, which means that you can say that for every y, which means that for every y belonging to the set of natural numbers and y not equal to 1, and y not equal to 1, we can set basically x equal to, we can set x equal to y plus 1, and or we can basically choose x as y plus 1 such that basically f of y plus 1 is equal to y. F of y plus 1 is equal to y, right? And of course you can see that also f of for 1 belonging to n, meaning that for this element over here, also you can say that for 1 belonging to n, we have basically f of 1, is equal to 1, and therefore f is basically onto, meaning that this way you can make sure that every element in the codomain of the function is the image of some element in the domain of the function. That means that in this case you can say that the codomain and the range of the function are equal sets, meaning that the codomain and range are the same sets. That is basically the codomain is equal to the set of natural numbers, and also the range is the set of natural numbers. Okay, so that was that. Now the next question that we have is example number 11, which is show that the function f from R to R, show that the function f from R to R, so basically the the domain and the range of the function is a set of real numbers defined as f of x is equal to x squared is neither 1 1 nor onto, is neither 1 1 nor onto. So what that means is that it's not a 1 1 function, meaning that basically meaning that if it's not a 1 1 function, then that means that if you have 1 2 3 and 4 and a, b, c, and d, then you could have basically, for example, some situation like this, means like, for example, the image of 1 is a and the image of 1 is b as well. And you can see it over here as well, meaning that if you have f of x is equal to x squared, f of 2 here is equal to 4, and f of negative 2 is also equal to 4. That means that in this particular function, apart from all the other elements in the range and in the domain and range, you have, for example, among all the other elements, you have 2 and negative 2, and both of these, and you have other numbers over here as well. And these two numbers are both basically simply mapped to 4 under f, right? And of course you can see it over here very clearly as well, because f of x is equal to x squared is basically this function over here. It's a parabola, and so you know that, for example, and you know that over here, for example, 1 2, it's mapped to this point, and 1 2, it's again mapped. Let's suppose that, for example, that's the same point. I was supposed to do it better, but these are the two basically parts of the function are supposed to be symmetric, and so 2 and negative 2 are mapped to the same output, and so the function is not 1 1. Now about the fact that it's not onto, well, there must be, as you can see, there is all of these elements over here in the range, in the codomain. There is all of these elements here in the codomain that have been left alone. Nobody has been mapped to them. They are the image of nobody. So that means that the function is not onto. But then we have to basically find a good, logical, reasonable way to write everything, all of this discussion down. Okay, so basically the line of reasoning that you can write for this is that basically, for example, you can argue that, well, this is f of x is equal to x squared, and the function would be something like this. Exactly, if this is 1 and this is 1 and this is 1, then you would get these points over here, so you would get basically some function like this and some function like this, and then basically you could argue that basically f of this is positive 1, this is negative 1, and this is positive 1. So you can say that f of negative 1 is equal to f of 1 is equal to 1, and well, you can say that basically f of you can, since f of x is equal to x squared, then f of negative 1 is equal to f of positive 1 is equal to negative 1 squared is equal to 1 squared is equal to 1, right? And therefore f is not 1, 1. And therefore f is not 1, 1. So you already know what 1, 1 means is that if basically you can say that f is 1, 1 if distinct elements of the domain have distinct images in the range or in the codomain. So you can see that you have these two distinct elements of the domain, negative 1 and positive 1, and the range and the basically the image of both of these distinct elements, the image of the two elements is basically one single element, which means that f is not 1, 1, right? Now, secondly, what that means is that, secondly, you have, for example, negative 2, you could say that the number negative 2 has been given as an example. So also the element, for example, negative 2, in the codomain R, codomain R is not image of any element x, is not the image of any element x in the domain, in the domain R. And then you can see that over here basically y or f of x is basically starts from 0 and goes all the way up to positive infinity, but all the f of x's or all the y's less than 0 are not simply a part of the range of the function. They are the part of the codomain. This whole thing, basically from negative infinity all the way up to positive infinity, they are basically the codomain of the function. Here you have your codomain. Your codomain is basically the set R, which goes from negative infinity to positive infinity. But the range of the function is basically goes from 0 to infinity. 0 to infinity, right? Which means that all of these negative numbers are not a part of the range of the function, which is basically, for example, which is to say that the element negative 2 is not a part of the range of the function, and so it does live in the codomain, but it's not an image of any of these elements in the domain of the function, right? And so therefore you can say that it's not a member of the range of the function, right? And so you can say that basically R is not, or F is not basically onto. Is not onto. Now, question number 12, or example number 12. Example number 12, we have basically show that you want to show that the function f from n to n, given by f of x is equal to basically x plus 1 if x is odd, and x minus 1 if x is even. So that is f of x is both 1, 1 and onto. it is both 1 1 and onto. Okay, so we have for all the basically for all the odd x's, f of x is equal to x plus 1. For all the even x's, f of x is equal to x minus 1. Which means that and we are working in the set of natural numbers, meaning that you would get some situation like this. For example, 0 is even, and so you would have your range. I mean that the function would give you a 0 over here. I mean at x is equal to negative, at y is equal to -1. For example, when y is equal to 1, since y is odd, since when x is equal to 1, then since x is odd, then 1 plus 1 is equal to 2. When x is equal to 2, since x is equal to even, 2 minus 1 is equal to 1. When x is equal to 3, since x is equal to odd, then 3 plus 1 is equal to 4. So that's basically something like this. And then for example, you can go for 4, and then since when x is equal to 4, since x is equal to even, 4 minus 1 is equal to 3. Something like this. And you can see that this thing keeps repeating itself all the way up to infinity. And I suppose if I go in this direction, the same thing will be all negative, meaning that, for example, if x is equal to -1, it's an odd number, so -1 plus 1 is equal to 0, right? If x is equal to -2, it's an even number, -2 plus 1 is equal to -3, which is this point over here. If x is equal to -3, an odd number, -3 plus 1 is equal to -2. -3 plus 1 is equal to -2. I suppose we made a mistake here. So -2 even -3. This is supposed to be right here. And so on and so forth, right? So this keeps repeating itself. This keeps repeating itself all the way up to infinity and all the way up to -infinity. And these are basically the outputs of the function. That's basically what this function is. Now you want to we want to show that it is both 1 1 and onto. So of course you can see that for every input that we have here, for every input we have some output, and all the input outputs are distinct. So that means that it is both 1 1 and onto, meaning that 1 1 means that basically all the distinct elements of the domain of the function has distinct images in the range of the function, right? And also it is onto because basically no element in the codomain is simply left alone. But then we will have to find some good way in order to write that down, right? Okay, so now in order to basically find a way to write down all of those things, so now this problem is we need to actually go back up here. It does need a little bit of patience. 138. And so basically the problem was so f basically was a function from n to n. F was some function from n to n given by this rule, which is basically f of x is equal to x plus 1 if x is odd, if x is odd, and it's equal to x minus 1 if x is even. And you want to show that f is both 1 1 and onto. Show that f is both 1 1 and onto. Now in order to do that, so first of all, in order to show that it's 1 1, you do need to, so basically in the argument that we had for 1 1 functions, we said that the function, we said that was definition number 5, and we said that a function f from x to y is defined to be 1 1, is defined to be 1 1, or injective if the images of distinct elements of x, if the images of distinct elements of x under f are distinct. So in simple language, what that means is that, for example, this sort of situation cannot happen. 1, 2, 3, and 4, for example, A, B, C, and D, and for example, suppose that this is mapped to this element, and this is mapped to this element, and this is also mapped to this element, meaning that f of 1 is equal to A, and also f of 3 is equal to A. If that's the case, then you cannot say that it's 1 1. Otherwise, if that's not the case, meaning that if every distinct element in the domain has its own distinct image in the range, then you can say that basically f is 1 1, meaning that if this is the case, so 1, 2, 3, and 4, for example, then you have, for example, A, B, C, and D, and then you have basically something like this. So meaning that every distinct element in the domain has its own distinct image in the range, that is 1 1. Otherwise it's many 1, right? Now, so if the images, if the images of distinct elements of x under f are distinct, right? So that is basically the condition that we talked about. And we also said that basically, are distinct. So you can say that is for every x1 comma x2 belonging to x, for every x1 comma x2 belonging to x, f of x1 is equal to f of x2 implies that x1 is equal to x2, right? x1 is equal to x2. So that is the condition that I can use, meaning that I can say that for every x1 and x2 belonging to the set x, if f of x1 is equal to f of x2, if that implies that x1 is equal to x2, that means that I'm talking about the same x1 and x2, meaning that the images are the same, and if the images are the same, the pre-images in the domain are also the same, then it's basically you're talking about the same basically pre-images, the same images. Then you're talking about just one point in the domain or in the range of the function, meaning that, for example, suppose that you have this function over here, and let's say that this is f of x is equal to x squared. Now 1 and 2 over here, and you can see that basically the image of this point, or of this element in the domain, is this point over here. The image of this point in the domain is this element over here, and they are the same, meaning that in this function f of 2 is equal to 4, 2 squared is equal to 4, and f of negative 2 is equal to 4, negative 2 squared is equal to 4. So here you can see that here f of x1 is equal to f of x2, f of 2 is equal to f of negative 2. This does not imply that x1 is equal to x2, because f of x1 is equal to f of x2, but then x1 is equal to 2 and x2 is equal to negative 2, and x1 is not equal to x2, right? So that means that in this case you cannot say that this function is 1, 1. It's many 1. But let's think about another function, for example. For example, f of x is equal to 2x. Another function, for example, f of x is equal to 2x. So 1 and 2, and the function is basically something like this. This is f of x is equal to 2x. Now if I take this point over here, you can see that basically this point is 1 and this point is 2. This is your domain and this is your range, right? Or you can say that this is your domain, this is your codomain. Now, let's say that f of x1 is equal to, let's say that f of x1 is equal to 2. And let's say that f of x2 is equal to 2, right? So here f of x1 is equal to f of x2 is equal to f of x2. That implies that x1 is equal to x2, because x1 is equal to 1 and x2 is equal to 1, right? So then in this case you can say that this function is actually 1, 1, because this function is 1, 1. Although, well, although basically you need to prove this logically, not using just one point in the domain of the function, but that's what that means, right? So now what we want to do is that we want to show that basically the same basically condition applies in the case of this function. We have f of x is equal to x plus 1 and x minus 1 for odd and even x's, and so let's assume that basically you know that basically your f of x is equal to basically again x plus 1 for odd x's and x minus 1 for even x's. Now if now in order to prove that this is the case, that f of x1 is equal to f of x1 is equal to f of x2 implies that x1 is equal to x2, you simply want to prove this. You want to prove that for every x1 and x2 belonging to x, you want to prove that f of x1 is equal to f of x2. That implies that x1 is equal to x2, right? So that means that, well, basically this is just a part of the condition. This is not important this is not important. I mean, this is not something that you need to prove, but you want to prove this statement in the case of this function. And this statement is made up of two statements. For example, let's call them P and Q. And so this is the same thing as P implies Q, right? So this is an implication, meaning that in order to prove that P implies Q is true, you simply assume that P is true, and then if you can prove that Q is true, then that means that P implies Q is true. Otherwise it's not. Otherwise P implies Q is not true. So what you want to do here is now basically make this an assumption that you want to assume that f of x1 is equal to f of x2 for this function, right? And if that is the case, then basically x1 and x2 can have 4 different cases. So the different cases that you could have is that basically x1 could be even or odd, and also x2 could be even or odd, right? And so what that means is that so if I enumerate these as, for example, 1, 2, 3, and 4, right? So then I can have these 4 cases as, for example, either x1 is even and x2 is even, x1 is odd, x2 is, or basically let's say that x1 is even, which is basically 1, and x2 is even, so that's a 3. Or I could have x1 is even, which is 1, and x2 is odd, which is 4. Or I could have x1 is odd, which is 2, and x2 is even, which is 3. Or you could have x1 is odd, and x2 is odd as well, 2 and 4. 2 and 4. So let's consider all of these cases. So now suppose that, for example, suppose that basically this is the case. I call it case A, I call this case B, I call this case C, and I call this case D, right? Suppose that A is the case, meaning that x1 is even and x1 even, and basically x2 is also even. x2 is also even. Now since I'm saying that basically f of x1 is equal to f of x2, let's see what happens when I make this assumption. So what is f of x1? What is f of x2? So if x1 is even, then basically I have to use this part of the function in order to know what happens to any output, right? So since x1 is even, then f of x is equal to x minus 1. Therefore you can say that f of x1 is equal to, basically using this part of the function, would be x1 minus 1. And since x2 is also even, then f of x2 is going to be equal to, again, x2 minus 1. Now since I'm saying that f of x1 is equal to f of x2, I can write x1 minus 1 is equal to x2 minus 1. These two will be cancelled out, and you have x1 is equal to x2, which means that basically, as I assume that f of x1 is equal to f of x2, that implies that x1 is equal to x2. That's the condition that I had here. And therefore, you can say that basically f is 1, 1. Right? So if you, as you can see, if you proceed logically, you can very easily work through the problem. Okay, so now let's say that B is the case, meaning that 1 and 4, so x1 is odd and x2 is 1 and 4, meaning that x1 is even and x2 is odd. x1 is, let's say that B is the case, meaning that x1 is even and x2 is odd, right? So let's say that that is the case. And over here again, I'm assuming that basically f of x is equal to f of x1 is equal to f of x2. Now, again, I need to calculate basically f of x1 and f of x2. So if x1 is even, then f of x1 is equal to x1 minus 1. F of x1 is equal to x1 minus 1. And f of x2 is going to be equal to x2 is odd. So x2 being odd is x2 plus 1. Is x2 plus 1. Now since I'm saying that f of x1 is equal to f of x2, that means that x1 minus 1 is equal to x2 plus 1, which means that basically what you can say that x1 minus x2 is equal to 2. Now here you can see that I have basically some x1 which is even, some x2 which is odd, and I'm subtracting an odd number from an even number. When you subtract an odd number from an even number, you will always get an odd number, meaning that, for example, you're subtracting an odd number from an even number. So for example, 8 minus 5 is equal to 3, or 16 minus 11 is equal to 5, or I don't know. You can have countless examples, but it's always like that. You'll always get an odd number. And over here, basically, we have x1 minus x2, which is an even number minus an odd number, and it's become an even number, which means that this is impossible. Which is impossible. Which means that basically, which means that this assumption cannot be made if x1 is even and x2 is odd, right? So the third part that we have here is basically, let's say that C is the case. If C is the case, then you have 2 and 3, meaning that x1 odd and x2 even. x1 odd and x2 is even. And so this is C is the case, right? So again, if x1 is odd, so again I have to make this, I'm making the same assumption that basically f of x1 is equal to f of x2. And what is x1 and x2 here, or f of x1 here? Basically, f of x1 is equal to x1 being odd. x1 being odd is x1 plus 1. Is x1 plus 1. And f of x2 being even, x2 being even is x2 minus 1. Is x2 minus 1. Right? Which means that if f of x1 is equal to f of x2, then I can write x1 plus 1 is equal to x2 minus 1. And so, again, you can say that basically x1 minus x2 is equal to negative 2, or you can say that x2 minus x1 is equal to positive 2. Again, over here you have an even number and you're subtracting an odd number from that, and you're getting an even number, which is like the previous case. So this is also impossible. Which is impossible, right? Which means that basically if x1 is odd and x2 is even, you cannot make this assumption. It's not possible. And over here we said that if x1 is even and x2 is odd, again it was impossible, meaning that if either x1 is even, x2 is odd, or x2 is odd, x1 is even, I'm sorry, if x1 is even and x1 is even, x2 is odd, or if x1 is odd and x2 is even, in both cases, basically it's not possible. And over here, both x1 and x2 were even, so in that case, basically, f was found to be 1, 1. Now, case D basically is 2 and 4, so that means that x1 is odd, x2 is odd. So that means that x1 is odd and x2 is odd. If that is the case, then if I assume that f of x1 is equal to f of x2, then basically what was the rule for being odd? X plus 1, right? So that means that f of x1 is equal to x1 plus 1, and f of x2 is equal to x2 plus 1. Which means that if I say that f of x1 is equal to f of x2, then you have x1 plus 1 is equal to basically x2 plus 1, which means that x1 is equal to x2, which means that basically f is 1, 1. So in both of these cases, where x1 and x2 were both odd, and x1 and x2 were both even, we found that basically f was 1, 1. And in these two cases, it was just simply not possible to make the assumption, so we do not have to consider those two cases. Which means that then you can say that basically which means that you can say that f is 1, 1. F is 1, 1. Right? So that is one part of the question. Now another part of the question is that you want to show that f1 is you want to show that f is you want to show that it's 1, 1 and also onto, right? So if you want to show that basically f is onto an onto function, what that means that what you need to do is that, let me use another color here. Now to show that basically f is onto, you need to show that every element in the codomain is image of some element in the domain. In other words, you need to show that basically the range of f is the same as the codomain of f. It's the same as codomain of f. Okay. So how do we do that? So basically what we need to basically show that for every now the function that we have is basically this function here. The function that we have is basically this function here. We have f of x is equal to x plus 1 if x is odd and x minus 1 is x is even. So we need to show that basically for every member of the set y, I'm sorry, for every member of the codomain, there is some element in the domain that is the preimage of that element, meaning that over here you have your domain, and over here you have your codomain, and you have all of these elements in the codomain. You need to show that for every element in the codomain, there is some element in the domain which is the preimage of that, element in the codomain, meaning that there exists no basically elements in the codomain that is not an image of some element in the domain, right? So how do we do that? So basically you can argue that so basically your function is basically f of x is equal to this function here, x plus 1, if for odd x's, if x is odd, and it's x minus 1 if x is even, right? Now, since I'm dealing with odd and even x's, I need to, if it was some situation like, for example, if basically the function had one single rule for all x's, it would be simpler, but that's not the case. So what I need to do is that I need to show that every even output has some element in the domain that is mapped to it, and I have to show that also every either even or odd element of the codomain has some element in the domain that is mapped to it, right? So what that means is that now if I say that basically f of x is equal to x plus 1, f of x is equal to x plus 1 for odd x's, what happens is that if x is odd, then basically you have an odd number and you add 1 to it. Then you have an odd number and you add 1 to it, you will get an even number. So that means that here your output, or f of x, is always even. Is always even, right? Now over here, when I say that f of x is equal to x minus 1, f of x is equal to x minus 1 for even x's, you have some even number and you subtract 1 from it, so you will get an odd number. That means that here f of x is always odd, right? So having these two situations, call it for example number 1 and call it number 2, you can take case number 1 and say that, for example, your f of x is equal to x plus 1, right? And you know that your output is always even because your input is always odd, right? So if f of x is always even, then we can assume that the output or f of x is in the form basically it's supposed to be even, so it is in the form 2r for some r belonging to the set of natural numbers. For some r belonging to the set of natural numbers, 2r becomes an even number. Now if I say that basically if I take this equation here and write it as basically if I assume that f of x is equal to y and then f of x is equal to x plus 1 here, then I have basically x plus 1 is equal to y, which means that x is equal to y minus 1, right? So which means that if f of x is equal to x plus 1, then I can write x as y minus 1, x is equal to y minus 1 here, and x is equal to again y minus 1 plus 1, so f of y minus 1 is equal to y. These two will be cancelled out. So that means that for any even output 2r, the input is going to be, well, 1 minus the output, right? The input would be basically 2r minus 1, which means that it is possible for any even output to belong to the range of or belong to the codomain of the function, and that even output will have basically some element in the domain of the function that is the preimage of that element, right? Which means that all the even outputs are now taken care of. So all the even outputs in the codomain will have some element mapped to them, which means that none of them will be left alone. Now, using the same argument, you can say that basically case number 2, using case number 2, we said that basically f of x is equal to x minus 1 for some even x. And here we said that f of x is going to be always odd. So some odd number would be, since the output is always odd, again we can assume that f of x, that the output is in the form is in the form basically 2r plus 1 for some odd number for some r belonging to the set of natural numbers. I'm writing natural numbers because I think we are basically actually working with the set of natural numbers, I suppose. So what that means is that now if I take this, basically if I take this equation here, and also if I assume that f of x is equal to y, so f of x is equal to y and f of x is equal to x minus 1, so I can write x minus 1 is equal to y, which means that basically x is equal to y plus 1, right? Now again, over here I had f of x is equal to x minus 1. Now x, if I take it as y minus 1, that means that f of y minus 1 is equal to x, which is equal to y plus 1 minus 1. These two will be cancelled out, so f of y minus 1 is equal to y. That means that for any basically odd output, case 2 here, which means that for any odd output 2r plus 1, then the input would be basically 2r plus 1 minus 1, right? 2r plus 1 minus 1, which is equal to 2r, right? 2r plus 1 minus 1, which is equal to 2r. So which means that it's actually possible for any odd output that you have in the codomain of the function, there is going to be some input in the domain of the function that is mapped to that element. That means that none of the odd outputs are left alone. All of the odd outputs are being an image of some element in the domain of the function, which means that over here we established that all of the basically even outputs are the image of some element in the domain of the function. Over here we established that all of the odd outputs are the images of some element in the domain of the function, which means that now every output that means that every output even or odd has some preimage in the domain of the function, and therefore f is onto, right? I just want to check my answer here. I'm not sure if I found this to be. So here it's saying that also any odd number 2r plus 1, it's supposed to be 2r plus 2, I suppose. Any even number 2r minus 1. 2r minus 1, that is correct, but there is something wrong here. Meaning that if I have f of x is equal to x minus 1, then if x minus 1 is equal to y, that means that x is equal to y plus 1. And so if f of x is equal to x minus 1, then f of, oh, that is a plus 1, right? That is a plus 1, and then over here you will get basically x, which is basically y plus 1 minus 1, so you get the y over here. So that means that basically over here, since I have a plus 1 here, so I have to add a 1 to that, you will get 2r plus 2. That's basically the right form of writing it. Otherwise, everything is right. So that's basically that was basically example number 12. And in the next video we will talk about 13 and 14. I'll see you in the next video. And thank you.